2 o'clock, which is unprecedented, but I have a meeting that I can't miss. So our speaker today is Bill Folkner. He did his PhD with Jean-Paul Richard and Joe Weber's group at the University of Maryland, so he got exposed to gravitational waves very early. He's been at JPL for some years, and he was the key person at JPL who pushed LISA forward, and a key person really in the United States who pushed LISA forward during the 1990s. He was the pre-project manager for LISA when the American studies were done at JPL. And he is now the project technologist, which is more or less equivalent to project scientist, for the LISA test flight, the American part of the LISA test flight, which is to occur in the middle of this decade. But he knows probably more than anyone else in this part of the world about LISA, so I'm real pleased to have him here to give the introduction.
Thank you, Kip. I'm not accustomed to giving classes. I'm much more accustomed to selling LISA as a project, and so I'm more into pretty pictures than equations and quantitative numbers, and so I hope you'll forgive me. I hope this is very informal, and if you have any questions at any point, please interrupt, because this is for you, not for me, and you're not providing any money or anything, so you might as well ask all the questions you can. Okay.
I got my checkbook right here.
All right, well, this is about, I think this is a $500 million mission, but currently they're planning to spend 3 times that. I mean, why not? So, I'd like to leave you at least with a broad brush overview of what the mission is currently, at least in my mind. I may be a little out of date. I haven't been following it on a day-to-day basis for about a year now. And some of the trade studies that go into the mission. So there are a lot of different effects that have affected the mission design, and I'm going to, and they kind of ripple through. Thermal behavior affects the optical bench, which affects the laser stability, also affects the proof mass noise, affects the telescope. So a lot of things are very interrelated, and so I'll try to hit on all of them, and the order may be not exactly optimal, but hopefully we'll see them all. But if you want to ask a question at any point, let me know. So what I'm going to end up with is trying to understand why this looks like this. Okay, so this is a slide which I'm not going to talk about sources of gravitational waves because that should have been done last term. So I just wanted to show this chart for a reminder and for illustrative purposes. Is there a pointer?
Yeah, there should be one.
Should have found that earlier.
What's becoming?
Thank you. Okay, so nothing I'm going to do here is going to be tremendously quantitative, and so this vertical scale in terms of strain amplitude I'm not going to mention very much. This is somebody's idea of what a typical signal-to-noise ratio of 5 curve might be, I think, for LISA sources versus LIGO sources. So the main thing I mention in talking about this chart is that the key frequencies for LISA observations is about 1 millihertz, 10 to the minus 3 hertz, whereas the key frequency for LIGO is about 10 hertz. It's about 4 orders of magnitude difference in frequency. And we always tell astronomers that's kind of like the difference between maybe an ultraviolet or infrared, or an infrared and a radio. There's a big difference in frequency between these sources. So it's worth spending the money to look into a different frequency regime. Another point on this chart is that there are a lot of sources probably, and they're all nearly continuous. They're almost on all the time. That's not quite so true for the coalescence of supermassive black hole binaries, where we expect to see them for a few months at a time maybe before they finally coalesce. But there will be hundreds and thousands of galactic binaries, maybe a few extragalactic binaries that will be visible to LISA. And there's this corner down here that Sterol Finney at least says is pretty well established, where there's so many binary systems in our galaxy that we can't resolve them. So that's different than the LIGO case. They're looking at transient sources with lifetimes of tens of seconds. So I hope Sterol Finney showed you this curve, but if he didn't, I'll show it for him, which is this shows the signal amplitude as a function of frequency for a hypothetical distribution of binary stars in the galaxy. So this is statistically based on observations of close white dwarf binaries, which are stars, not neutron stars, but white dwarf binaries in close orbits with orbits of a period of an hour or shorter. So statistically, there's a lot known about the existence of these binaries. A few of them are actually known and observed, but there's expected to be many, many thousands of them. And the point here is that at some frequencies here, there will be accountable number by LISA. LISA will have a frequency resolution of sort of 1 over a year in terms of frequency. So where sources are spread apart more than that, LISA can see them one by one. At lower frequencies, these become so closely separated that LISA can't separate them. It can't estimate the 6 different parameters for each source that's necessary to characterize it, because there's more signals in the frequency resolution bin than can be allowed for the 6 parameters. So there's a noise. So this looks like a noise for LISA. There's just so many sources we can't tell them apart, and it still boggles my mind trying to detect gravitational waves for 20 years, and we haven't seen one yet. There's too many. There's too many. So the only way we could resolve those better would be to have a longer mission, or to have a much larger orbit, much larger than 1 AU, so that the period of rotation was larger, and that would give us some directionality that would allow us to separate some of these. But it's sort of a logarithmic problem. So for every factor of 2 we gain in terms of mission duration, for instance, we can go from maybe there to there. It's just a very small amount in terms of sampling sources in terms of the galaxy. But the existence of this background is an important effect. Okay, I want to show some historical view graphs, which they're obviously scanned and copied and scanned and mailed. Okay, but people back in 1978 were saying, well, if you could do gravitational waves in space, what would you do? So this is a picture, I think, from Ray Weiss in '78, saying, well, you can easily have a kilometer arm in space, and the vacuum is free, so why not build LIGO in space? But it's very expensive to put a kilometer arm in space, and it's probably cheaper to do that on the ground. So this idea evolved very quickly, I think. For many years, Peter Bender at Colorado, JILA, it's called, Joint Institute Laboratory for Astrophysics is what it used to be called, now it's just JILA. He came up with this idea for in space, well, what you really want is long arms, right, to go for this low frequency window that's very different than anything you can do on space. And his idea was to have 3 spacecraft, 1 central spacecraft here that would have some reference point and send laser beams out in 2 directions to end spacecraft. And these spacecraft would have to be not just mirrors to reflect the signal back like in LIGO, but to actively measure the incoming signal, coherently lock a laser on it, and send it back. Because otherwise the signal to noise ratio drops like the distance to the 4th power. It's a very strong effect. So by doing this local detection and transponding, is what we call in the radio world, then you go only an R² loss. You pick up an enormous factor. So this is Pete Bender's idea, which he kicked around for a long time, and it's changed from this for a couple of reasons into something like this. So this is what the original LISA concept looked like back in 1993 when we proposed it to a space agency for the first time, and that space agency was the European Space Agency. And at that time, you can see there's still the 2 arms, but we decided as a team that we would break that central spacecraft into 2 different spacecraft. And there's 2 reasons for thinking that way. One is that if this spacecraft and that spacecraft and that spacecraft and that spacecraft are all the same, then we can build them all to the same drawings, build them all to the same specifications. We think that should lower the cost. If you have to build 2 different kinds of things in space missions, it's very, very expensive. So that's one reason to break the central corner into 2. The other thing is that it was realized by looking at this orbits, the possible orbits for all of the spacecraft, that the angle between these 2 spacecraft was going to change as a function of time. It wasn't always going to be a fixed angle. And so by having the spacecraft broken in 2, there's a natural degree of freedom for pointing corrections due to orbital changes. And then we clearly have to correlate this length with that length, and so that's why there's a laser beam here in the back. And so we studied this for several years. ESA decided they could do that, but it would cost much more than the mission category we had originally proposed for, which was called a medium-sized mission, or M3. That was the 3rd medium mission we proposed that for. But it was much too expensive for that, and eventually they selected a gamma-ray telescope, I think. But in the meantime, they opened up a possibility for a mission that was double that mission cost, called the Cornerstone mission. And so this idea was proposed as a cornerstone mission to ESA in 1996, and it was accepted. So that's the first time LISA really got on anybody's official roadmap, was with the ESA selection of a cornerstone mission. And for the cornerstone mission, the science team said, well, let's be a little more grandiose than the simple Michelson interferometer, and let's propose a 6 spacecraft constellation. And I think a lot of the credit behind this idea goes to Ron Hellings at JPL, who was trying to figure out a way to do missions very cheaply. And his concept was, well, if you had 6 spacecraft, then you could treat any one of the pairs as the vertex of the interferometer. And if you built your spacecraft really, really cheaply, then maybe you could tolerate the loss of a spacecraft, and then no matter which spacecraft you lost, you would still have a working interferometer. Okay? But also, if every spacecraft is working, then this interferometer arrangement has some advantages in that since any pair can be the center of vertex, you can think of this Michelson and that Michelson as being independent Michelson interferometers, and they detect then different polarizations of gravitational waves. With any one Michelson interferometer, you're insensitive to a gravitational wave that passes in the direction that goes along the distance between them. So by having this other one, you can detect that polarization. The third option then gives you a third Michelson, which doesn't give you anything linearly independent from the other two, but it does allow you to add the signals around this way versus that way to make a big Sagnac interferometer. And the Sagnac interferometer is insensitive at low frequencies to gravitational waves. And so that's a way of calibrating the instrument noise source, which is something we weren't sure how we were going to do with just 4 spacecraft, how we could tell what the measurement system noise was versus a background of gravitational waves, either from galactic binaries where there's so many we can't count them, or maybe a stochastic background from the early universe, like the 3-degree thermal background in the electromagnetic spectrum. So this has a lot of advantages to doing this. This evolved. The problem with this is that the European Space Agency is much more conservative than NASA was a couple of years ago, and they were never going to adopt the idea that you could lose a spacecraft. ESA is not going to lose a spacecraft, period. So having 6 spacecraft is twice as expensive as having 3 spacecraft. And so we evolved towards this geometry in the end, where we tried to preserve all the nice features of, in terms of signal processing of the 6 spacecraft mission, where we could choose any vertex as a Michelson and have the Sagnac, because that was always desirable, but combine everything within a single spacecraft at each vertex. So there's still some redundancy in terms of if there's some problem with some component in here, you would still have a Michelson from the other corners. But we can't tolerate the loss of the spacecraft anymore. So this concept we worked on for quite a few years. 1998 is when we did the first study at JPL, and this has been the basis of the mission as far as I know till today. Whoops. Let's see if I can do that.
I think your arrow keys will do it.
Okay. All right, so this is another LISA curve, sensitivity curve, and this is going to look very much like a LIGO curve, where at the bottom here we're limited by the shot noise, just as probably LIGO is dominated by shot noise. I hope that's right. And then at shorter frequencies, you have nulls in the response, where the wavelength is a multiple of the separation between the spacecraft. Here, those nulls are mutated into wiggles because you're never in any particular direction for very long with LISA, and all the signals are on for a long period of time. And so when you average over what this interferometer is over a long period of time, you get dips rather than, absolute nulls. And then at low frequency, analogous to seismic noise or thermal noise in the test mass for LIGO, we have noise forces on the reference test masses. So this basic U-shaped curve is something we worked on for a long time. And we've talked about why choose that limit, why choose that frequency, why choose that particular shape of the U. Yes?
What noise sources do you have on the LISA spacecraft? Are they getting hit by some gas or what?
I'll talk a little bit more about the noise sources on the test masses in a while. If we just had a test mass in space, it would see the sunlight. All right, so the sun would push on it with a force of about, I don't know, a micronewton, 10 to the minus 6 of a newton would be about the force, within a factor of 100 or so. And it fluctuates about a part per thousand. Just the output of the sun fluctuates about a part per thousand every 1,000 seconds, which is the millihertz frequency. So that would be a huge effect. Okay, there are other effects. If it built up a charge, then it would be a charged mass moving through the sun's variable magnetic field, and that would be another effect. Those might be the biggest ones if we just had a free test mass. But there are other effects due to components near the spacecraft. So I'll get more to that in a minute, but don't let me forget. Let me talk more about the shot noise and the interferometer noise to start with, and I'll talk more about the test mass noise at the end, because that's something that's very challenging to try to quantify and actually assure we can get it. The shot noise limit we've chosen for LISA is sort of this 10 picometers per root hertz, which is much, much coarser than the LIGO actual distance scale measurements, which are sort of 10 to the minus 19 meters per root hertz. So we keep telling our review boards that this is easy, except that we're doing it 4 orders of magnitude lower in frequency, where we have a lot of 1 over F noise to worry about, for instance. But the position noise then turns into a strain when you divide it by the length. And so the one nice feature here to remember is that the strain sensitivity in terms of the sensitivity curve is independent of the length, because the distance noise divided by the distance is the strain. It's independent of the length. What's important then is the diameter of the telescope and the amount of laser power it can have and the wavelength of the laser. So we need a monochromatic single mode laser just like LIGO does, and so we're planning to use the 1064 nanometer wavelength just like LIGO does. And we think that in a space version of that laser we can get a 1 watt laser, and with an overall quantum efficiency of 30% by the time we go through all the optics. There's about a dozen different optics we have to go through. We think we can get a 1 watt laser. So the diameter of the telescope is mainly the big free parameter to play with here and trying to push down the LISA sensitivity. And the diameter of the telescope we've chosen here is 30 centimeters, and that's for 2 reasons. One, we know from the Hubble Space Telescope that a 3-meter mirror is really expensive, and we don't think anybody would pay for that. It might be cheaper now, but the Hubble telescope was $3 billion back in 1980 or something. So we picked that because it looks more affordable. The other thing is that's the biggest telescope we thought we could fit in the launch vehicle that we're normally using, because we have to have 3 of these spacecraft and we have to stack them all up on a single launch vehicle, and that was the biggest mirror we thought we could fit. It looks like we might be moving to a bigger launch vehicle now, and so this number might get bigger to run this all down smaller, depending on what the cost and the mass and everything is.
Bill, how hard is it to increase the efficiency of the optical system? I mean, what's the limiting factor there that makes that only 30%?
One thing is the laser wants to be isolated from back reflections, and so a Faraday isolator is often used with a 1 watt laser to minimize back reflections. And those things, there's some kind of crystals with AR coatings, and they're about 90% efficient. Then you have to run it through a phase modulator to modulate some signals on the laser beam. I'll talk a little bit more about in a minute. Then we have to run it off a beam splitter into a photodetector. The photodetector efficiency is about 0.8. When you just take all these 0.8s and 0.9s and you multiply 10 of them, you end up with 0.3. So unless we can raise the efficiency of everything from like 0.8 to 0.95, then we're going to be stuck with around this 0.3. Maybe we could eliminate some of the optics. I'll show you more about the optics layout in a minute. Okay, so I talked about the telescope diameter as maybe being the free parameter that would allow you to push this down or not, lower. But I wanted to show you what the effect of the arm length was, because this is a discussion we've had a number of years ago, and we've had it over and over again, and it's going to come up again in the next few years as we try to make LISA more real here. So the white line is the nominal LISA strain sensitivity. This is in per root hertz. There's a nice web-based calculator for generating these curves now. I don't know if everybody has that kit, but I could send that. You're on the science team, you must have seen that. So I just did this yesterday, in fact. If you had 5 times longer arm length, we used to say that lengthening or shortening the arm just moves the U back and forth, but that's not quite true. Lengthening the arm pushes this corner to the left, or pushes it to the right if you shorten it, but it pushes this curve up and down. So a shorter arm length actually gives you a broader sensitivity region, and a longer wavelength gives you a shorter one. But the longer one obviously gives you better sensitivity at low frequencies. So why choose a longer one or a shorter one or an intermediate one? Well, the big factor is the galactic binaries. They're not shown here, but the galactic binary background that we can't tell from noise is lying around here. Okay, and so that's a severe problem, and it might imply you to push for pushing the shorter arm length, except a lot of the sources that we're really most sure of are sort of 10 or 100 million solar mass black holes coalescing. And their frequency, your final frequency, is over in here. So if you pick this, you'll have a low signal-to-noise ratio for those, whereas if you pick the white one, you have a signal-to-noise ratio of hundreds, and here you'd have thousands. Okay, but because the galactic binary limit comes up about here. And so we think the white curve is a reasonable choice of a mean baseline that gives us a fairly broad spectrum of things that we can look at. We have reduced sensitivity here where we don't know that we have high priority science sources there, although it's something we're always worried about. Pushing lower gives us some better sensitivity down here where we're have a little more confidence of getting supermassive black holes, but the cost of being able to do science in here. So that's one of the free parameters, is that baseline length, and it's still being discussed.
How much easier would it be to build a shorter arm length?
How much?
How much easier would it be if the arm length would be shorter? Like you would need smaller mirrors.
No, remember, to first order, the shot noise is independent of the arm length. So if you keep the same size mirror, just keep the same size laser power. If you put it closer together, your distance noise is improved. You have better sensitivity, but your arm length is shorter. So when you divide by the arm length, you have the same fractional strain sensitivity as if with the longer one. Okay, so as long as you're keeping the spacecraft mirror diameter and laser power the same, you can change this arm length however you want. It doesn't affect the cost at all. It doesn't affect the bottom of that curve. It just affects where and frequency you're optimized. Okay, so the first order doesn't make anything more expensive. In practice, I think going to a shorter arm length probably makes it a little more complicated, and I'll get to that in a minute. Okay, the pointing is going to be a little harder. Some things will be harder. Some things will be better.
I thought you can, the diameter of the laser beam would be smaller when it reaches the space.
I'll let you work this out on the problem set.
Yes.
It all drops out, as Bill says.
I tried to write an
Exercise for you.
The spot is smaller, so you receive more photons. And so your signal-to-noise ratio in terms of photons is better, right? So when you turn signal-to-noise ratio into a phase measurement and multiply by the wavelength of the laser, you have better sensitivity in terms of distance. Okay, but in terms of gravitational wave amplitude, it's not you get a displacement that's proportional to the distance between the spacecraft. And so it turns out you come out of a wash. Okay, so that would be a good homework problem, is to work out this shot noise thing. And I tried to do it yesterday, I just ran out of time. So that's why I chickened out and just did the one parameterized curve. Okay, so the orbital geometry. This is something I'll probably spend quite a bit of time on. The orbital geometry, we want 3 spacecraft, and it's advantageous to have the distance between the spacecraft remain as constant as possible, for a reason I'll explain in a little while. For a simple Michelson interferometer, you really want the distance between the spacecraft to be the same, and LIGO actually feeds back forces to the positions of their test mass to keep them at the same distance. In terms of what orbits we can actually have, it turns out we can have some distances remain roughly the same, but we can't have the triangle remain equilateral without applying fairly big forces. So we're going to have some changes in forces. This particular geometry, where they're inclined here with respect to the ecliptic, which is the orbit of the plane of the Earth's orbit around the Sun, declining the orbit plane with respect to that by 60 degrees gives you a stability here that's much better than if you kept them in the plane, by a factor of the eccentricity of the orbit squared. And so it's a huge advantage to have this triangle formation with this inclination to the ecliptic. And that, the idea of this orbit, really due to Peter Bender again. Now, so that's the 60 degrees. This angle 20 degrees behind the Earth is a bit confusing because people say, well, 60 degrees is a Lagrange point. But in fact, this isn't particularly at a Lagrange point. It's not meant to be stable. This 20 degrees comes about as it's just an engineering compromise. This triangle is slowly distorted by the tidal attraction of the Earth. So having this angle better makes that distortion less. That distortion is not so big, and I'll show you that in a moment, at 20 degrees. If we brought it into a few degrees, it would be big. The disadvantage of having this angle bigger is that the distance to the Earth gets bigger, and the cost of communicating data back from the spacecraft gets bigger as we make this angle bigger. It's also more expensive in terms of spacecraft propulsion system to get it far away from the Earth. So this 20 degrees is sort of a compromise on those 2 or 3 issues. Now, I wish I could have animated this, but I couldn't figure out how to do it in PowerPoint. Each of the spacecraft is in their own elliptical orbit around the Sun. Okay, so this orange dot here is always in its freely elliptical orbit around the Sun nominally. Okay, so no forces are applied. It just always orbits the Sun like that. The others are in their own individual orbits around the Sun. So there's nothing pushing on the spacecraft to make them stay in this triangle. It's just that the initial conditions of the orbits around the Sun are very cleverly chosen so that when one's above the ecliptic, the other's below, and 180 degrees across, this one's below and this one's above. And so it's this clever choice of orbit arrangements keeps these arm lengths relatively constant as a function of time. And if you looked at this constellation trailing the Earth, then the triangle would slowly rotate once per year, or you'd see this triangle rotating around following the Earth. Okay, but it's not really being driven to rotate, and it's not being driven to stay in the triangular formation. It's just a clever choice of the orbit initial conditions. And that's only really possible when the inclination of the orbit is this 60 degrees. So it's a very clever choice of orbits. There's some advantages to this orbit. One is that the sunlight always hits the spacecraft plane. We call this the spacecraft plane. The sunlight's always at the same angle as it goes around the sun. If you're the sun, it slowly rotates, but the angle between the normal to this surface and the sun is always the same, and that helps in the thermal stability quite a bit. And it also helps us shade the optics so the sunlight never goes in the optics. Another advantage of being about a distance from the Earth is 1 AU, the distance from the sun of 1 AU, is that it's a fairly inexpensive orbit to get into. It actually would be better, I think, for Lisa to move this out to 5 AU, the orbit of Jupiter, but the natural temperature of things out at 5 AU is colder, right? Jupiter's average temperature is colder than the Earth. And so you'd have to expend power warming everything to get up to room temperature where most of our electronics work, just kind of by lucky coincidence. And we'd also have to work harder to generate power because the sunlight's 25 times less intense. And it's also much more expensive propulsively to get out there. So the 1 AU is a fairly natural choice for that reason. Okay, the spacecraft orbits are not adjusted as a function of time. And so the spacecraft, the distance between them varies as a function of time. And I told you that this choice of orbits minimizes that, but it's still significant. So this is for what I call the nominal orbits. I don't know if this has changed, but I think this is the best choice of orbits. This shows the arm length as a function of over 5 years for the 3 different arm pairs. So spacecraft 1, 2, and 3, you've got 3 different arm lengths. And you can see that we've chosen these orbits to keep the variation range kind of small for 2 of the arms, and it's bigger from the 3rd one. And it turns out you can average this out, so the peak variations for the 3rd one are smaller, but you can only reduce that by about a factor of 2 at the cost of making the other 2 much worse. So to avoid that, you would actually have to drive the spacecraft positions. And we're worried about driving the spacecraft positions because we're worried about the influence that would have on noise on the test masses.
So if you had only the sun and nothing else in the solar system except Lisa, would these separations be constant?
The effect of the sun, we've chosen these because for the first 6 months, the rate of change of 2 of the orbit arm lengths is almost constant, okay? And that for the first 6 months.
Is it perturbations for pull of Jupiter, or is it something intrinsic to
when the first year is over, see, they spread apart after 6 months and then they come back. If the Earth wasn't there, this would repeat. Okay, so this pattern would repeat.
So that's intrinsic. Is it due to the non-circularity of the orbit?
Yeah, the fact that they're elliptical.
The fact that the orbits are slightly.
Well, that's right. So this term, it turns out, is the distance times the eccentricity squared. Okay.
Now, why are the orbits slightly elliptical? Can you make them?
If you had every orbit in the plane, it's easier to think in the plane, and you want one spacecraft to be inside the orbit and the other one outside and in reverse, then they have to be elliptical.
Okay, so it's the ellipticity that's causing the dominant effect.
That's right.
It's not perturbations of the gravitational poles of the planet.
So the gravitational pull of the Earth dominates. Okay, Jupiter and Venus is not as big, but they're not insignificant. And how much the effect they have then is seen on the growth of this as a function of time. So this growth is a function of time as the tidal pull of the Earth. So that would be smaller if we moved it further from the Earth. But we always have to have at least one of the arms doing this size of things. And you can see that the size of this thing doesn't change very much, right, over 5 years. It would take 20, 30 years to see for this to grow to the point where it would dominate the natural motion. Okay, so like I say, we could minimize this over a 5-year mission. We could reduce the peaks by a factor of 2, but we give up the fact that we have 2 arms nearly identical for the first 6 months. Okay, and I'll explain in the next chart why that is. And it turns out that for small adjustments in the spacecraft position, 1 a month, a very small impulse every month, we could actually keep these 2 tracking each other, okay, for a small penalty in terms of propulsion. But we're not sure that we want to do that. By choosing this particular set of orbits, we keep that option alive for at least 6 months. until we find out whether we have a problem or not. If we find out we have some problem that we can't solve any other way, we could actually fire the rockets every month and then to keep the two arms here the same length. We would give up a lot. We don't think we're going to have to do that, but it's a possibility. And it doesn't cost very much to do that. Okay, so the big problem with the rate of change of the arm lengths is that it causes a Doppler shift in the laser frequency. So if we have a laser here generating a laser light at a frequency of 3 times 10 to the 14th hertz, and it goes out to the other spacecraft. Treat the other spacecraft as just a mirror in your mind, and it comes back again. If there weren't any rate of change of the arm length, then it would come back at exactly the same frequency you sent it out. But because there's a rate of change, there's a Doppler shift in the V over C. So that V over C Doppler shift, it doesn't take a very big V over C to get a pretty appreciable rate if the frequency of the laser is 3 times 10 to the 14th hertz. So we need to remove that Doppler shift by a frequency standard in order to compare the incoming Doppler shifted laser to the local laser light to do our our interferometer measurement. So how good of an oscillator can we get? Well, the state of the art is about 10 to the minus 16 in terms of Allen deviation. And have you talked about Allen deviation? All right, thank you.
Talk about Allen variance.
Allen variance. Allen deviation is the square root of the Allen variance. Allen deviation is used more often. John, correct me if I'm wrong. 10 to the minus 16 is about as good as you do with a hydrogen maser. There's some hope of doing better with a linear ion trap. There's some data to show that you can do about a factor of 10 better. It's taken 20 years to go from 10 to the minus 16 to 10 to the minus 17. So there's not a lot of hope for getting a better frequency standard, but it would be useful in some cases. The best oscillator flown has an Allen deviation of about 10 to the minus 13, which is an oven-controlled crystal oscillator. So there's a big difference between what's already been flown and what's available on the ground. Flying a hydrogen maser would be a big task, whereas these linear ion trap standards may in fact be viable. Okay, so what is the effect on the distance noise if you have an Allen deviation of 10 to the minus 13? If you have to assume something about the spectral shape of the oscillator, but this is for a flat Allen deviation as a function of time, goes something like this. And for a 5 meter per second arm rate, which is sort of the average of what I showed you before, this is the laser frequency. Then you get a 5 megahertz Doppler shift, and for the 10 to the minus 13 oscillator, that's 2 times 10 to the minus 9 meters per root hertz. So it's about a factor of 100 better than we'd like to do for LISA. It's 100 times larger than the shock noise we've talked about nominally. So we have to get rid of this somehow, and our choices are either to fly a better oscillator, or another way to do that is to actually modulate the lasers, modulate this clock signal, whatever your local oscillator is, maybe a 10 megahertz clock for your timing standard. You can modulate that onto the laser beam, send it out, get it back again, and compare it to what it was a light time earlier. So this is sort of a delay line stabilization method for clocks that actually has been used many times before. And that's the nominal plan for LISAs to do this clock cancellation technique. So we have to have not just the laser carrier, but this modulation on top of it. And having to have this modulator is one of the reasons why we have the lower quantum efficiency, because the phase modulator introduces another loss. So I don't know if Bob Sparrow will talk about this anymore, but that's about all I wanted to say.
A little bit again.
Oh, you get it. Sorry, Bob. Okay, and another consequence of the orbital change is that the direction from one spacecraft to each of the other two subtends an angle that's nominally 60 degrees. Ideally, it would be an equilateral triangle. But in fact, it changes as a function of time. And so that means the spacecraft has to point. And remember, back when we originally proposed LISA, we had two separate spacecraft so we could absorb that angular change. But we now know about how big that angle is about plus or minus a degree or half a degree as a function of time. And so our payload has to accommodate this plus or minus half degree of motion within the single spacecraft structure now. However, there's an effect of pointing error on the position measurement. And that's because the output of our telescope is not a perfectly spherical wavefront. If we had a perfectly spherical wavefront, then no matter how we pointed at it, the perceived phase delay of the other spacecraft would always be the same. We're expecting a perturbation on that due to the finite size of the mirror and the finite quality of the mirror. And so there will be an error then in terms of wavefront phase at the other spacecraft depending on how the spacecraft pointing is varied. All right, and LIGO has a similar term. So This is an equation that gives sort of the size of that effect. If we assume a lambda over 20 mirror, this should be 30 centimeters. I apologize for the typo. If we have 5 nanoradian pointing offset, so we have this parabolic offset from a perfectly spherical wavefront. Okay, if we were right on the center of that parabola, then small offsets would average out. If we're off from the center of that parabola by 5 nanoradians and jiggle around it with 5 nanoradians per root hertz noise, then we come out with about 10 to the minus 11 meters per root hertz. Okay, so we have to not only point at different spacecraft with a different angle as a function of time, but we have to find where the center of this parabola is and keep locked on it and jitter around it very little. So this is pretty demanding. It turns out that LIGO and the other ground-based interferometers have to have this jitter number fairly small anyway. And so there's a number from the 30-meter interferometer at Garking. They've done this 5 nanoradian per hertz noise pointing accuracy at a millihertz at Garking. This number is a little harder to come up with. Okay.
So just for our thinking, 10 to the minus 11 meters per root hertz translates into a strain spectral density that is about the least.
This is the shot noise limit. It's 10 to the minus 11. Right. So the shot noise limit we can't get away from. Right. We have to have the shot noise unless we go to quantum non-demolition or bigger mirrors or something. So we'd like to have everything else be smaller. Okay. So we'd like to do a little bit better than this. Okay. If we do worse than this, then this will dominate the error budget. Okay. Another effect on the pointing problem is that the distance between these spacecraft is long enough that the round-trip light time is significant. And so if I'm over here and I want to point at my laser at the other spacecraft, I need to point to where it's going to be 16 seconds from now, because that's where it'll be when my light beam gets there. So I have to point ahead of it, essentially, by an angle of about a half a microradian. And originally the science team thought, well, that's okay, we'll just rotate the beam splitter on the optical bench a little bit and that'll suck that up. Except this angle that the orbits tilt in changes as a function of time. So this pointing angle actually changes out of the ecliptic plane by plus or minus a half a microradian over a function of time. And as far as I know, we haven't really solved this problem yet. Okay.
I think it's now a factor of 10 larger.
Of course.
That pointing angle.
But it's easy enough to compute. You just know the velocity of the spacecraft and figure out how to do it. There's a test mass with if you have a square test mass, you can kind of tilt that as a function of time, which is not a very attractive option, but maybe the best one. So this point ahead angle is an important problem, I'd say, to be solved. Okay, I want to say a little bit about why did we choose that orbit, why didn't we choose some other orbit? I told you these orbits are very nice in terms of having nice constant solar pressure, solar thermal input. They're very triangular as a function of time, has a lot of nice properties, but couldn't you think of something else? Of course you could think of something else, and one idea that has been worked on a lot by Ron Hellings at JPL is to have a triangular formation in the plane of the Earth's orbit around the Sun, with a distance between the Earth and the spacecraft a couple times the distance to the Moon. That's supposed to be the Moon, that's supposed to be the Earth. Okay, the advantage of this orbit is it's a lot cheaper to get to. Okay, it takes a much smaller rocket and much smaller propulsion system on board to get to it. The penalty is that the perturbations in this orbit are much bigger than from this nice solar triangle orbit by more than a factor of 10. So that means accommodating the pointing variations, accommodating the frequency, everything's at least a factor of 10 harder, but not necessarily impossible. The problem is that this constellation, in my mind anyway, is that this constellation rotates around the Earth with an orbital period of about 50 days. So that means this line is going to rotate with a period of 50 days. Okay, so that means at some time it's going to be pointed right at the Sun. Okay, and a lot of the time it's going to be pointed near the Sun. So getting rid of sunlight on this is a very daunting problem. It looks like you could build an optical filter to cut out enough sunlight that it wouldn't raise the shot noise. The problem is the sunlight's going to hit this optical filter and some fraction is going to be absorbed, and that's going to be, the Sun's output is variable, and the angle that this has to the Sun is variable, and so the temperature coefficient of this filter looks prohibitive to me, but it's not been proven yet. If you could do that, that might be a cheaper way of doing LISA.
You say it's a 50-day period?
50-day period.
That's sort of low frequency.
Well, Ron Hellings always argued that was out of band, although in fact there are solar luminosity fluctuations that are in band at a millihertz. Also, I'm not sure that the thermal response is out of band. There are some long thermal time constants in here and how they interact. It just scares me, but you could think about doing this. So this is another possible orbit.
Why is it you can't?
Why not tilt it by 90 degrees?
Perturbation is too strong, or what is it? Yeah.
If you tilt this triangle so it's out of the plane of the ecliptic, then it turns out it's almost as expensive as getting to least orbit in the first place,
I see.
right? Plus you have 10 times more perturbations on top of it. So this is an orbit that's been kicked around, and mostly it's been kicked out, but it's just worth thinking about other ideas to see if anybody has a clever idea. Okay, another thing about the orbits. So another good thing about the orbits is that because this triangle is tilted with respect to the ecliptic, then it changes as a function of time. And so the antenna pattern of the interferometer has some nulls in it for any particular polarization. There's some nulls. And I apologize, this is a fuzzy diagram, but it's the best one I had. So that antenna pattern changes as a function of time, and that changes as a function of time because our sources are on all the time. The change in the antenna response as a function of time allows the amplitude of the signal to be modulated, and that modulation then tells you something about the direction to the source in the sky. This is not as strong an effect as the fact when you're orbiting around the sun, the constellation is orbiting around the sun, it's moving towards the source part of the year and away from the source, the other part of the year. So that's very much like pulsar timing. Have you had a talk about pulsar timing? Okay, so it's very much like the pulsar timing problem. You can get at least one component of the position very accurately by watching the plane or the timing change when the expected phase of the arrival of the signal is. And that works because the sources are on all the time, or at least many, many months. You also learn something about the out-of-plane component, but the amplitude contributes to the out-of-plane component significantly. So these two things are actually good things in terms of they give us the directions to the source, and the accuracies that we can get to the sources for the strongest sources are sort of like a degree, and that's a disappointingly large number for trying to look at events like the coalescence of supermassive black holes. We're going to be able to see them with LISA. We're going to be able to predict the time that's going to happen to seconds. It'd be nice to have a telescope pointing at it, but we can only get the pointing direction to it to about a degree ahead of time, which is bigger than the field of view of big telescopes. So it'd be nice to figure out some way to do the pointing better than that. As far as I know, nobody's figured out how. This is just a response as a different time of year for two different sources to show what the effect of the amplitude modulation is. Okay, yes. Pause.